Hey class, welcome back. We're wrapping up chapter 8. So this is the last lecture for chapter 8, and we ended our last lecture. I just slightly introduced limiting reactant, theoretical yield, and well, I just said that we were going to learn about these, and we are. Okay, so we're going to go back to this pancake example. All right, we're drawing a comparison between the recipe for pancakes, where we have flour, eggs, and baking soda as our reactants. Okay, so I'm just going to write reactants, right? And then the pancakes are our products, all right? And the coefficients, right, in front of our reactants are the same as the coefficients in front of every other reactant that we see in a balanced chemical equation, and the same for the coefficient in front of the pancakes, the 5 pancakes for the products. Okay, so we're drawing a comparison, and what we're going to do is what I'm going to do is introduce and show you how to calculate limiting reactant, theoretical yield, and this thing called percent yield. All right, so again, limiting reactant we already talked about slightly. Conceptually, we covered it, meaning that we know that the limiting reactant in a reaction, right, determines the amount of product that is made. And it determines the amount of product that is made because it is the reactant that runs out first. Okay, so you'll see here in this chemical reaction, right, that is the making of pancakes, we have 3 possible reactants. And so the question is, which one of these, right, the flour, the eggs, or the baking powder, is the limiting reactant, all right? Is the one that's going to produce the least amount of pancakes. So what you want to do is first you need to start off, you have to have, having the balanced chemical reaction is only one piece of the puzzle. You need to have a certain amount of starting material, right? So what I mean by that is, suppose we have 3 cups of flour, 10 eggs, and 4 teaspoons of baking soda, right? That's your real world example. How many, and you want to make pancakes for your family, how many pancakes can you make? Well, you have to take the fact that you have 3 cups of flour, right? And from the balanced chemical reaction, I'm going to do that a little bit smaller. From the balanced chemical reaction, we know, from the coefficients specifically, that for every 1 cup of flour, put 1 CF for cup of flour, we get 5 pancakes, right? Which will give us, if we, essentially units cancel, answers left in pancakes, that's going to give us 15 pancakes. Right? That's a situation where if we had 3 cups of flour and enough of the eggs or the teaspoons of baking soda, will give us 15 pancakes. Likewise, if we have, again, 10 eggs, now we have to convert eggs using the balanced chemical reaction to pancakes. So according to that, for every 2 eggs, right, we get this from the coefficients, 2 eggs gives us 5 pancakes. So again, PC pancakes. And so collectively, before we units cancel, right, that's going to give us 25 pancakes. Now we're going to do the baking soda. So for 4 teaspoons of baking soda, that's how much we have to work with. We convert baking soda to pancakes. Baking soda, we should say, to products using the balanced chemical reaction, which is the coefficients are 0.5. I'm going to say baking soda, right? BS. And gives us 5 pancakes, PC. units cancel. Answers left in pancakes, which is what we want. And that's going to give us 40 pancakes. So in order to figure out the limiting reactant, right, you're going to have to always convert every single reactant, in this case flour, eggs, and baking soda, to product, and in this case it's pancakes, using the coefficients from the balanced chemical reaction. Okay, so again, you have two things, right? You have what you start off with, which is this 2 bits of information. You have what you start off with, which is this, and then you have the balanced chemical reaction. And those two things will help you determine the limiting reactant, right? So here I took what we started off with, which was 3 cups of flour. I converted it to pancakes, 15. And basically, long story short, what you're going to look at is you're going to evaluate each reactant and see which reactant is the one that's going to make the least amount of pancakes. And in this case, that is the flour, right? Because the flour makes 15 pancakes, while 10 eggs will make 25, and 4 teaspoons of baking soda will make 40 pancakes, okay? So since flour, in this situation, 3 cups of flour will only make 15 pancakes. Flour equals limiting reactant. So just to let you know, LR is going to be limiting reactant from here on out. Okay, so flour is the limiting reactant. All right, so let's take a look at what is theoretical yield. Okay, theoretical yield, this slide's a little bit messy, so let's just move down. So this is kind of a nicer slide. So now we're looking at theoretical yield. We've already identified the fact that flour is the limiting reactant because it gave us 15 pancakes, right? The theoretical yield of a reaction is is essentially doing what we did here. It's taking the limiting reactant and converting the limiting reactant to product, okay? That's essentially assuming that if everything goes right, when you use 3 cups of flour, you should get out 15 pancakes. So this 15 pancakes is our theoretical, so I call it theo yield. All right. So again, the limiting reactant in this situation, because we converted every single reactant to product, we determined that the cups of flour is our limiting reactant because it makes the least amount of pancakes. It's going to be the reactant that runs out first when we do this balanced chemical reaction or perform it, right? And the theoretical yield is the limiting reactant converted to product. Okay, so in theory, when we use 3 cups of flour, we should get out 15 pancakes. That is why, in theory, it's our theoretical yield. So this is all just saying the same thing, right? If this were a chemical reaction, the flour would be the limiting reactant for the reasons that I just mentioned, and 15 pancakes would be the theoretical yield, right? Now, what about percent yield? So now that we know how to determine a limiting reactant of something, we know what theoretical yield is. What about percent yield? So suppose we cook our pancakes and we accidentally burn 3 of them and 1 falls on the floor. So even though we were supposed to have 15 pancakes, we only finished with 11. All right. So these 11 pancakes would be called our, and I have it down here too, actual yield. If this were a chemical reaction, the 11 pancakes would be our actual yield. It's the amount that we actually made, which is I'm just going to keep reading, the amount of product actually produced by a chemical reaction, okay? So we have theoretical yield, limiting reactant, and then we're still trying to understand what percent yield is, okay? But what we just introduced to you is we just introduced actual yield, which is going to be crucial in calculating percent yield. So percent yield is the percentage of the theoretical yield that was actually attained. All right, so if we know our actual yield, which was 11 pancakes, and if we know our theoretical yield, which was 15 pancakes, we can calculate percent yield by taking the ratio of the two and multiplying by 100. And that will give us about, here it is, 73% yield. So, according to this recipe, if you have 3 cups of flour, you can make 15 pancakes, right? And enough of everything else. You can make 15 pancakes. So say you try to make 15 pancakes, but you only end up with 11. That means you have a 73% success rate, essentially. 73% of the theoretical yield was actually produced, okay? The actual yield of a chemical reaction must be determined, right? This is really important. The actual yield must be determined experimentally. And since this is a lecture class, you will always be given actual yield because you can't actually run a chemical reaction in a lecture class, okay? So actual yield of a chemical reaction will always be given to you because it is normally determined experimentally. The actual yield is almost always less than 100%, and that is because of human error. It's very hard to sit back and say, oh, I did everything perfectly. You know, reaction conditions have to be perfect. Extraction purposes or purification techniques, all that stuff has to be perfect in order to actually have 100% yield. Again, this is most of the time it's human error, but it also can be that it's just not a very good reaction, right? Product is lost in the process of recovering, all that stuff. One of the things that you also need to know for percent yield is if you get something that's greater than 100%, that means you also did something wrong, because you can never really, get more than what you should out of a chemical reaction. So there's that. Okay, so to summarize, limiting reactant or reagent, again, those two terms are interchangeable, is the reactant that is completely consumed in a chemical reaction. It determines how long the reaction goes and how much product is formed. All right. We figured out how to determine a limiting reactant. Let's zoom in. By converting each reactant to product using balanced chemical equation. Okay, so we determined the limiting reactant by converting each reactant to product using the balanced chemical equation, and the reactant that determines the least, or that produces the least amount. So I'm going to zoom in again. Amount of product is your limiting reactant. Okay? So, oh, that's ugly, but that's an arrow. So again, the limiting reactant and that's how you determine it, by converting each reactant to product using the balanced chemical equation. The reactant that produces the least amount of product is your limiting reactant. Theoretical yield, okay, is the amount of product that can be made in a chemical reaction based on the amount of limiting reactant. So by essentially determining the limiting reactant, you're also calculating the theoretical yield, okay? Because the amount of product that you actually produce from, the amount of product that can be produced but from the limiting reactant is your theoretical yield, okay? So these two are essentially in the same calculation. We also talked about actual yield. Actual yield will always be given, and it is the amount of but you have to know what it is and how to use it. It's the amount of product actually produced by a chemical reaction. And then percent yield is the formula where you have actual yield over the theoretical multiplied by 100%. Okay, and it's the amount, it's the yield, it's the percentage of the theoretical yield that you actually produced. All right, so let's do some examples, put some, give this some more context, okay? So if you guys remember, we already talked about this problem. Solid zinc reacts with hydrochloric acid to produce aqueous zinc chloride and hydrogen gas. How much zinc chloride is produced from 1.528 grams of solid zinc? So here, what I did in this, we already talked about this previously, okay, in lecture, this problem. But I essentially told you that solid zinc is the limiting reactant, right, in this reaction. And I told you that solid zinc, 1.528 grams of solid zinc produces 3.185 grams of zinc chloride. Okay, we did this in a previous. So what is this called? So we know that solid zinc is the limiting reactant, but what is this called? This is called the theoretical yield. Now, all right, it's the amount that should be made from 1.528 grams of solid zinc. So let's say you take this, you're like, okay, you run this reaction and you're assuming that you should get every time you run a reaction in a chemistry lab, you should know how much you should actually get out. Okay, so if you're looking at 1 gram or 4 grams of product, that's a big difference. So you need to have that calculation down before you start any other reaction, or before you start isolating the product, so you can have a good idea of what you should be looking for, okay? So let's say you go into the lab, you run this reaction, and you already calculated the theoretical yield before you got started, and you're like, I'm looking for about 3 grams of product, all right? So you run the reaction, but here's the deal. You only isolated 2 grams, all right? You only isolated 2. What is your theoretical yield? Well, first you also need to know that, oops, I'll do that here. You also need to know that 2 grams is your actual yield. Okay, so if you need to calculate percent yield, you're going to take percent yield is equal to the ratio of actual yield over theoretical yield multiplied by 100. All right, so since our actual yield was 2 grams, our theoretical yield was 3.185 grams. Take the ratio of the 2 and multiply it by 100. And of course, I don't know why I forget to get my calculator out. So we're going to have 2.00 divided by 3.185. And then we're going to multiply that by 100. It looks like we only get about 62.7%. So that's actually not that bad. 62.79% of your theoretical yield you actually got out. Okay, so that's how you would calculate percent yield from a chemical reaction. So let's do a bit more. Lots more practice. All right, so limiting reactant and percent yield, right? That's what we're calculating, but we're doing it mole to mole calculation. All right, so first, write a balanced chemical equation for the reaction between solid titanium, so titanium, and chlorine gas. Chlorine is a diatomic to form titanium 4 chloride. It's a solid. All right. So first we need to make sure that that is balanced. Now right off the bat you can tell that it's not because we have four chlorides here. Why do we have 4 chlorides? Because it's titanium 4. All right. So since we have 4 chlorides here and we only have 2 here, we're going to have to put a 2 right here to balance it. Okay. So it is now balanced. If we begin with 1.8 moles of titanium and 3.2 moles of chlorine, what is the limiting reactant and theoretical yield? So what you're going to have to do, again, is you're going to have to convert reactants to products using the balanced chemical reaction. We start off with I'm going to zoom in. We're going to start off with this one right here, 1.8 moles of titanium. And we're going to convert it to product using the balanced chemical reaction. The coefficients of titanium is 1, and the coefficient for titanium chloride is 4. So it's going to be 1 mole Ti over 1. I'm going to zoom in a little bit more. 1 mole. All right. So obviously this is a 1-to-1. But I'll just show you just to make sure you understand. Remember, units cancel. We're left in mole titanium chloride, and we're going to get out 1.8 mole titanium chloride if we started off with 1.8 moles of titanium. Now we're going to do the other reactant, 3.2 moles of chlorine. So again, 3.2 moles of chlorine. I'm going to zoom in again. Convert it to moles of product, and according to our balanced chemical reaction, for every 2 moles of chlorine, we get out 1 mole of titanium chloride. So moles chlorine cancel, answers left in mole titanium, and so we're basically, so we're end up with 1.6 mole titanium chloride. Now that we've converted both reactants to products, we're going to sit back and we're going to look and say which one produces the least amount of product. Turns out that's right, chlorine, because 1.6 moles is less than 1.8. So Cl2 is limiting reactant. I'm just going to circle that. Okay. So chlorine gas is the limiting reactant because it will only produce 1.6 moles. So essentially it's going to run out first. Right? Then we're going to ask, so we just figured this out. The limiting reactant is is chlorine gas. All right. And what is the theoretical yield? Well, We already did that. We killed two birds with one stone by converting this. Theoretical yield is 1.6 mole. Right, because we took the appropriate amount of starting material, which is 3.2 moles of chlorine, and we converted it to moles of product, and that's what we got out. So the theoretical yield is 1.6 moles, and chlorine is our limiting reactant. Okay, and the reason why we call this, again, a mole to mole conversion is because I started off with moles of reactant, and all you had to do was convert to moles of product. Here's another example. Write a balanced chemical equation for the reaction between solid sodium. So we have solid sodium, Na, and fluorine gas. Again, fluorine is a diatomic, it's F2. Both of these guys are in their elemental form, okay? So a metal, solid metal, that's elemental form. Diatomic, F2, gas, elemental form, all right? To form sodium fluoride, NaF. Pretty sure that's a solid. Okay, so write a balanced chemical reaction. Is this balanced? The answer is no, because we have two fluorines here and we only have one here. So we're going to have to put a 2 there. And now, since we have two sodiums on the product side, we're going to have to put two sodiums on the reactant side. Now that is balanced. Okay. Again, this is another mole to mole conversion, okay? Because we are beginning with 4.8 moles of sodium and 2.6 moles of fluorine, and we need to know what the limiting reactant is and the theoretical yield. So we're going to go back and we're going to convert 4.8 moles of sodium right, 4.8 moles of sodium to product. So according to our balanced chemical reaction, for every 2 moles of sodium, so it's still a 1-to-1, we're going to get out 2 moles of sodium fluoride. I didn't put mole there, so mole cancels, right? And we're going to get out 4.8 mole. Okay. Now we're going to take 2.6 moles of fluorine, convert it to product using the balanced chemical reaction. And according to the balanced chemical reaction, for every 1 mole of fluorine gas, we get out 2 moles of sodium fluoride. Okay, so that will give us 5.2 mole moles of sodium fluoride. So now you're going to, again, we are determining the limiting reactant. So now you're going to sit back and you're going to ask yourself, well, which number is higher, 5.2 or 4.8? And obviously it's going to be 4.8. So what reactant gave us 4.8 moles? Sodium. Okay, sodium gave us 4.8 moles. So since sodium gave us 4.8 moles of sodium fluoride, which is less than 5.2 moles from the fluorine gas, then we're going to say sodium is our limiting reactant. Okay, so I'm going to put, and our theoretical yield is going to be the amount that can be produced. All right, so our theo yield is 4.8 mole. Okay, 4.8 moles of sodium fluoride. All right, so we're going to take this a step further, and instead of doing just converting straight from mole to mole, we're going to do mass to mass, because again, mass is something that we can actually work with in a lab, right? Not necessarily moles, because we can weigh out, we can determine mass using a scale. All right, so 3 grams of ammonium react with 5 grams of oxygen to form nitrogen monoxide and water. How many grams of nitrogen monoxide, is formed, right? So first we have to do is write, and I have it kind of right here for you, write a balanced chemical reaction if it's not given. All right, so we're going to do that right now. Ammonia is NH3. It's not ammonium, right? Oxygen is a diatomic, it's O2. Nitrogen monoxide is NO, and water is obviously H2O. So we're going to say NH3, I'm not worried about phases right now, plus O2 goes to nitrogen monoxide plus H2O. All right, so now we have to balance it. I'm going to start from the left to the right. Nitrogen, I have 1 here, and I have 1 here, so it looks like nitrogen is good. That's my little check mark. I'm going to zoom in. Oxygen, we have 2 oxygen on the reactant side and 2 oxygen on the product side, so it looks like oxygen's good. But I skipped hydrogen. So hydrogen, H3, right? We have 3 on the reactant side and only 2 on the product side. So what we're going to have to do is find a common multiple. That is going to be 6, right? So in order to get out 6 hydrogens, I have to multiply this by 2. In order to get out 6 hydrogens over here, I'm going to have to multiply this by 3. And what does this mess with? This essentially messes with our nitrogens now and our hydrogens. So let's go back to our nitrogen. I have 2 nitrogens here now, so I'm going to have to put a 2 here. Okay. Now, how many oxygens do I have? So I'm going to get this smaller. How many oxygens do I have on the reactant side? I have 2, and on the product side I have 4 oxygens plus 3 oxygens, which gives me a total of 7. So here's the thing. No, I'm sorry. I have 4. I have 2 oxygens, which is going to give me a total of 5. Okay, 5 oxygens. So here's the deal. There's nothing that I can multiply this by to get to 5. Okay, so what are we going to have to do? Well, watch this little trick. So remember, so I have a 2 here. So let's put a 4. Let's just double everything. I have a 3 here. So let's do 6. And I have a 2 here. So what I'm doing is I'm doubling all the coefficients. So if I double the coefficients, now everything, my atoms are still balanced. All I did was double everything that I've had so far, right? But the difference is instead now I have, instead of 5 oxygens, what do I have? I have 10. So 4 plus 6 equals 10 oxygens. And that is a multiple of 2. So there you go. So let's double check everything now. Start from left to right. Always double check your work. 4 nitrogens here, and I have 4 nitrogens here. So nitrogen is good. I have 12 hydrogen here, and I have 12 hydrogen here. So hydrogen is good. I have 10 oxygen, and we already went over the fact that I have 10. So all of my atoms are now balanced. So that's a really good trick. All right, so remember when I did that and why I did it. Okay, so now that we have a balanced chemical reaction, now we can determine the limiting reactant. Considering the fact that we have 3 grams of ammonia and 5 grams of oxygen. So we only have 2 reactants, okay? So what I'm going to do is I'm going to convert 3 grams of ammonia to product. Well, which one? The one that's specified, nitrogen monoxide, okay? So you are going to have to, let me see if I have enough room here now. All right. Sorry, I didn't leave enough room here, so I'm going to have to zoom in. So let's do ammonia first. Convert 3 grams of ammonia to product. So I'm going to zoom in. So 3.00 grams of NH3. Now we're going to convert it to product, but the first thing we have to do is we have to convert ammonia to moles, and we need the molar mass of ammonia. And I'm quickly opening up my computer and I'm typing in molar mass. Sorry that this is molar mass of ammonia is 17.03. So I'm going to put 17.03 grams per 1 mole NH3. Okay. Then what I'm going to do is I'm going to convert from, now that I'm in moles, I can use the coefficients from the balanced chemical reaction. So again, here, for every 4 moles of NH3, we get out 4 moles of nitrogen monoxide. All right, so when you are converting to determine the limiting reactant, you can stop at moles. You don't have to stop, you can stop at moles. You don't have to convert directly to grams, okay? So 3.00 multiplied by 1 over 17.03 multiplied by 1 over 1. So we have 0.176, mole all right. So we have 0.176 moles of nitrogen monoxide from 3 grams of ammonia. All right, now we're going to do the same thing with the other reactant, which is oxygen. Okay, so oxygen, we start off with 5 grams. O2, we have to convert it to moles, so we need the molar mass of O2, which should be 32, so 32.00 grams per 1 mole O2. And now that we are in moles of O2, we can convert to moles of nitrogen monoxide using the coefficients from the balanced chemical reaction. So again, 5 mole under 4 mole NO. And again, like I said, you can stop at moles here because we're converting to the same product. I just did that, so it's a little bit better to, that was a little sloppy, my separation. Okay, so 5.00 multiplied by 1 over 32.00 multiplied by 4 over 5, and that gives us 0.125 mole NO. So, which one is the least amount? 176 or 125? 125 is the least amount. So what is our limiting reactant? It's oxygen, okay? So oxygen is our limiting reactant because it produced the least amount of product. So now we have to determine the theoretical yield. So in order to do that, you're going to convert moles of product to grams to determine the theoretical yield, right? Because we want to know what the theoretical yield is in grams. In grams. So what you're going to do is you're going to take 0.125 and you're going to convert moles of NO to grams. And again, you need the molar mass of nitrogen monoxide. And it's 30.01 grams per 1 mole NO. So 0.125 moles, 30.01 is going to give you, we're going to work with, that's going to give you 3.75 grams of nitrogen monoxide. So what is your percent yield if you isolate 3.8 grams of nitrogen monoxide? So our theoretical yield was only supposed to be, it was only supposed to be 3.75. For some weird reason, you isolated. For some weird reason, you isolated a little bit more than that, 3.80. So what you're going to have to do, and that's okay, right? I mean, sometimes that happens. I think that that's what happened when you guys did your zinc iodide reaction. You actually isolated more than what you should have, all right? So that's not a big deal. But what you're going to do is you're going to take your actual, so this is your actual, right? 3.80 is your actual. This is your theoretical, so you're going to take 3.80 grams over 3.75 grams, and you're going to multiply that by 100. Okay. Just making sure all my math is right. Sometimes if something screws up and I did something wrong and I didn't catch it and you guys are like listening going, she did this wrong, sorry. It should be okay, but you know, not everybody's perfect. Okay, 101%. So that is a little bit higher than we would ever have wanted, but still, that's what the numbers say. So a percent yield is going to be 101. All right, so what did I do? Let's go through it. First, I did a balanced chemical reaction, okay, made sure to balance it. Then what I did was I determined the limiting reactant by converting moles of reactant to moles of product. Okay, so I did that here and here, all right? And the reactant that gave me the least amount of product was O2. So O2 is my limiting reactant, right? So then what I did was to determine the theoretical yield, I took the moles of product that I got out of 5.00 grams of oxygen, and I converted that to grams of nitrogen monoxide using the molar mass of nitrogen monoxide. Okay? So that is my theoretical yield. And then I took percent yield. I got my theoretical, which is in the denominator, and then my actual yield, which was given, is in my numerator. Take the ratio of the two and then multiply it by 100, and that is my percent yield. Let's do another one. The balanced chemical equation for the reaction between solid copper oxide and copper 1 oxide and solid carbon is, so let's write it out, solid copper oxide. So I'm not going to necessarily worry about the phases, but so copper 1, right? So if it's copper 1 and it's oxide, there has to be 2 coppers, right, for every 1 oxygen, plus solid carbon. And what is that going to go to? Well, basically what is going to happen essentially, if you think about it, okay, sorry, I didn't make sure that that was what I was reading correctly. So essentially what's going to happen is, remember, this is copper, hold on just real quick. All right, so remember, this is copper plus 1. Plus 1. There's 2 of them. And then you have oxygen, which is a 2 minus. And then you have plus carbon, and you can't really do anything with that. So essentially what's going to happen is the only thing that can happen is this is a single displacement reaction, essentially, where copper is going to replace, carbon is going to replace copper. And I'm not going to necessarily give you something like this. This is just an example, all right? That would be kind of hard for you guys to determine at this point, but this is what's going to happen, all right? So you're going to make carbon monoxide plus solid copper, all right? And then this has to be balanced because there's 2. I'm just going to go ahead and delete this, all right? There's not really anything else that you can get out of that, so just bear with me. Okay, so now that we have the balanced chemical reaction, when 11.5 grams of carbon react with 114 grams of copper oxide, how much solid copper is formed? All right, so we need to figure out what so we're converting every reactant to product, all right, and this particular product, how much solid copper is formed. So we're going to take, first, just because it's there, 11.5 grams of carbon, convert that to moles of carbon. So for every 12.01 grams of carbon for every 1 mole. And then we're going to, now that we're in moles, we can take the coefficients from the balanced chemical reaction. So every 1 mole of carbon, we get out 2 moles of Cu2O. And that, let's see, 11.5, 1 over 12.01, multiplied by 2 over 1. I hope everybody's with me on this. You're not just like listening to me like mumble to myself. All right, so that's going to give us 1.92 mole copper oxide. All right, now we're going to take 114 grams of I'm sorry, not copper oxide. Now we're going to take 114 grams of copper oxide, convert that to moles. All right, so the molar mass of copper oxide is 143. 1 mole. And now that we're in moles, we can use the coefficients from the balanced chemical reaction, which for every 1 mole, right? So for every 1 mole of copper oxide, we get out 2 moles of solid copper. All right. So again, when we're determining the limiting reactant, we don't have to convert all the way to grams of product. All right. We just need to get to moles of product, and then we can determine the limiting reactant from that. So 114.5 multiply 1 over 143.10 over 2 over 1, multiply by 2 over 1. And that is going to give us 1.60 mole copper. So, because 1.60 is less than 1.92, our limiting reactant is copper oxide. Okay. A lot of students have a lot of problems with I'll see on certain exams that they'll put, oh, this is the limiting reactant. No, just because this is the least amount of product doesn't mean that this is not a reactant, right? If this is the least amount of product, then this is the limiting reactant. So copper oxide is the limiting reactant, okay? And then to determine the theoretical yield, you're going to take that's a copper. So 1.6 mole, 1.60 mole copper, and you're going to convert it to grams. Okay, and you're going to convert it to grams using the molar mass of copper from the periodic table. So for every 1 mole of copper weighs 63.55 grams of copper. And you should get out, so 1.60 multiplied by 63.55, that's going to give you 101.7 grams of copper. So that is your theoretical yield. Okay. So this was again, a mass-to-mass conversion, but when you are determining the limiting reactant, right, which is what we did here, even though you're given grams of starting material, which you were here and here, okay, you convert it to product, you can stop at mole product when you're determining the limiting reactant. Okay, you can stop because you can compare, since we're in mole copper here and mole copper here, it doesn't matter if you convert it to grams or not. You can easily determine that 1.60 mole is going to be less than 1.92 moles. Okay, so copper oxide is our limiting reactant, and our theoretical yield is going to be 101.7 grams, because we took this number right here and converted it to grams of copper. All right. So this is just the same thing. This is for you guys to understand the relationships that were used, so you can go through that and read that for yourself if you'd like. This is another example, or this is the same thing, it's just all together. So now we have, okay, so again, our theoretical yield. Oh, I guess, and basically what this slide is, and I included this for you guys later on, but let's say you isolated 87.4 grams instead of 100 when you should have gotten 101.7. To calculate the percent yield, you're going to take the actual, right, over the theoretical again. So this is the actual, right? This is the theoretical, which we already calculated. Take the ratio of the two and multiply by 100, and we end up with 85.9% as our percent yield. Okay, so I think we're finished. Yeah, we're done with chapter 8. We're going to start solutions next. Sorry, I'm scrolling through this to make sure. So I'll go ahead and I'm going to upload this right now, and then we'll meet on Tuesday and talk about limiting reactant, percent yield, and theoretical yield and all that stuff. Okay, thanks for listening.